Let's continue with our parametric equations. So suppose you had these equations here and you wanted to try and figure out, well, what's the graph look like? What is it in x and y's? Did anyone come up with any suggestions? What could you do here to eliminate the dependence on t?
Divide by 6.
Divide by 6. All right, so that's one way. X over 6 equals sine squared, and y over 6 equals cosine squared. Then what?
X over 6 plus y over 6 equals 1.
Yeah, add them together. X over 6 plus y over 6 equals sine squared plus cosine squared, which is 1. In other words, x over 6 plus y over 6 equals 1. Let's multiply both sides of this expression by 6. Kind of clean it up a little bit. So if I do that, I multiply everything through by 6, then that'll give me a little bit cleaner equation, x plus y equals 6. Yeah, you can move the x over and put it in slope-intercept form. Another way you could have done this, just kind of a quick FYI, is if you did x plus y equals 6 sine squared of t plus 6 cosine squared of t. And I think Julian's saying, oh, man, yeah, I see it now. What happens to this term on the right side? That just becomes, yep. So that whole thing gets replaced by a 1. And you end up the same equation as before. X plus y equals 6. So a lot of ways you can do that. Now keep in mind, as you're looking at this parameterization, both of these are squared. So can any of these, either of these ever be negative?
No.
No. The smallest that they could be is 0. The largest they could be is 1. So 1 times 6 would be 6. So this is really trapped in the first quadrant between 6 and 6 on each respective axis. Let's take a look at the graph here on Desmos. So let me turn that on. There you go. Actually, let's just do this here, right? So zooming in on this a little bit, as I move from s equals 0 to s equals 2 pi, wow, look at that. Most of this is wasted, right? It's like, well, what's going on? It's just, once you get to 1.5, that's it. But what you're not seeing, and let's move this back here, is what's happening kind of beneath the hood a little bit. Let's turn on this point, and now let's vary it so we can see a little bit more about what's going on. And after we get to 1.5, what happens?
Goes back.
Oh, it's starting to bounce back and forth a little bit. So you're getting a little bit more motion out of this than we first realized. So cool. And with different parameterizations, you can make that motion look different. You can speed it up, you can slow it down. You can use it to model whatever you need. Ben?
How do you find, like, what would you do for the orientation for that?
Yeah, for the orientation on that, I'd have to probably limit you to maybe pi over 2.
So you wouldn't have something.
Because that one's going back and forth a few times. So the orientation would just be one direction to make it a little bit easier on you. Yeah, it's a good question. I don't think I would ask. In fact, I'm promising I won't ask you to work with the orientation of something like this from 0 to 2 pi. So just to make it a kinder, gentler math class. Any other thoughts on that one? All right, so here's the equation, but you're really only getting part of that equation, right? You're just getting the part that's in the first quadrant. That's all. So now there's different ways to parameterize this. If I wanted to use this parameterization, in fact, this is kind of a lead into the next one. So let's take a look at this, and let me come up with a different parameterization. So I could say y equals 6 minus x, and if I wanted to come up with a parametric form, I could very easily. Let's just do it the very simplest way. Let's let x equal t, and then if x equals t, then I can say, oh, well, y equals 6 minus t. And that's a parameterization of this right here. It's kind of like a cheap way to get a parametric form of that equation. So your pairs of points are going to look like t and 6 minus t. That's what you would graph on Desmos. This is what you would put into your graphing calculator. So now you've got a parameterization for that line. Now it may not match perfectly the parameterization you had just a minute ago, but that's okay. So here's your parameterization right here. And if you move this around, you'll see that, oh yeah, you do get this. If you wanted to match exactly, you'd have to figure out, all right, well, what value do I need to start at? Looks like I need to start at t equals 0 and keep that up until I get to, I don't know, t equals 6. Yeah. So from t equals 0 to t equals 6, if I make that cut, 0 to 6, and yeah, 0 to 6. How come I'm getting something else here? I shouldn't be getting the stuff here. Oh, there we go, 0. There we are. So now I'm getting exactly what I wanted, 0 to 6. Just that little part that I had with my equations up here. So nice. Let's keep that in mind as we work through example I. Comments or thoughts on this last one? So we nursed it for a little bit of extra stuff. That's good. Let's take a look at example I. I want to do kind of the same thing with example I that I did with example H. That is, I want to come up with a parametric equation with this. I want my graph to start here and end here. So, I guess the first thing I can do is come up with just a regular x and y equation and then play around with it from there. So how would you start working with x's and y's? How would you find an equation of a line that goes through these points? All right, so let's use the 2 points given. Just a reminder, the slope is y2 minus y1 over x2 minus x1. Thank you, squared. All right. Say again?
It's 9 over 5.
9 over 5? All right, let's see. So in terms of my points, I've got the points 1 and 0, and 6 and 9. So plugging that in here, it's going to be 9 minus 0 over 6 minus 1, which is 9 over 5. FYI, that's also 1.8. So that's my slope. What else am I going to need here? Well, you might need this one. Y minus y1. Anyone remember this one? Come on, a few of you should. How about somebody on Zoom land? What's the rest of it? Equals what? Just unmute yourself. Equals m times x minus x1. That's the point slope version of the equation of a line. So let's pick one of the points here for my x1 and y1. I don't know about you, but I'm liking the simpler point. Why not? You don't get bonus points for making it hard on yourself, so let's choose 1 and 0. So it's going to be y minus 0 equals m, which is 9/5 or 1.8 times x minus 1. And if you solve for y, it's just y equals 1.8 x minus 1.8. Great. So that's an equation in x and y. But I wanted something in terms of t. And I wanted to start here and end here. So how could I do that? How could I write this in terms of t? Sure, let x equal t. If x is equal to t, shake. What would y have to equal? if x is t, then what does y become?
Wouldn't it also be t, or would that be? I think it's y.
Well, if x is t, then you can replace that with,
Oh, you're gonna replace it with the 1.8 x times 1.8, right?
well, but you need to replace that, right?
Yeah, so that would be t.
1.8t minus 1.8. And now, that's a pair of functions that both depend on t. So there's your parametric equation. Nice. The only thing left we need to do is we need to figure out, well, where are we going to start and where are we going to end with our t so that we start here and end here. That's the last thing we need to figure out. So, okay. Well, I guess there's a couple ways you can do that. And the easiest one is working with the x coordinates. Why is it easiest to work with the x coordinates? Well, because the x coordinates, x equals t, right? So what should I let t vary between?
1 and 6.
1 and 6. 1 is less than or equal to t is less than or equal to 6. That should start out here and trace things out in this direction. Beautiful. Beautiful. Let's see that that actually worked. So that's down here at example I. Here's your equation in x's and y's, but I don't want that. I want it in terms of t's. So that's this right here. Let me kind of go back to this. Let me just do a b here. No, it didn't give me, it didn't give me a slider. Sorry. All right, so 1 to 6. Sorry, it's not giving me a slider right now. Let's just try that one more time. Try F. There we go. So slider will do from 1 to 6. And bam, perfect. So it starts out right here at 1, 0, and it ends at 6 and 9. Perfect. Comments or thoughts on that one?
So that's just working backwards instead of you having the parametric equation like what we were doing before.
We started out with the x and y equation and came up with the parametric equation. Exactly. So we're going to do that one more time. Are we okay with this one? Let's take a look at this one. This is an ellipse. So we can come up with the equation for the ellipse kind of by working backwards a little bit. I know that in the x direction, that distance is 2. And in the y direction, that distance is 4. So I can do this. I can say, all right, well, I've got x over 2 squared plus y over 4 squared equals 1. Okay. Looking good there. Now I need to come up with something for x and for y. So here's the thing. When I divide my x by 2 and when I divide my y by 4, I want things to cancel out so that when I divide by 2 and divide by 4, I'll have a sine squared plus a cosine squared or a cosine squared plus a sine squared equal to 1. So let's try and think about this. What could I put in the numerator of this so that when I divide it by 2, I end up with either a sine or a cosine? 2 sine of t. All right, that'll work. And for y, I have to put in y equals
4 cosine.
4 cosine of t. Beautiful. But those aren't the only solutions I can come up with. So that's one solution. What's another parameterization? What else could I do here? How about -2 sine of t? Because when I square it, you know, when I cancel out the 2 and square it, the negative is going to disappear. So, okay, that'll work. And y would equal, I could still leave this as 4 cosine of t. That'd be a different parameterization. Or I could make them both negative. Doesn't matter. Can anyone think of anything a little bit more unique and different? Yeah, I'll put the negative in there. What's that?
Oh, x equals 2 sine t. No, 2 cosine t.
Yeah, 2 cosine of t. And y equals 4 sine of t. And last one, we'll do x equals -2 cosine of t and y equals -4 sine of t. And there's a couple more, there's a lot more variety that I could put in here as well. This is just a couple to get you started. But to show you there's a lot of different possibilities here. All of these different possibilities are each going to have their own orientation. It just kind of depends on which one you choose. I think I've got that one diagrammed down below. So let's go to example J. And let me first start by turning on all these points. 1, 2, 3, 4. Now 2 of them happen to be starting out at the same place, but they're going to go in different directions. So there we go. Now you got all 4 points. So 3 of these are going clockwise. Let's see. 3 of them are going counterclockwise. One of them is going clockwise. Okay. So a couple of these one of these has different orientations, but they're all going to match overall this function here. Pretty cool. So depending on which one you choose, it's going to have a different orientation. You can use your orientation to match what you need in terms of whatever specific application you're working with. Awesome. How are we doing on this one? Let's call it a day for section 6.7.